have learned a lot from previous speakers. So today I would like to introduce you a new method for strongly correlated electrons. It's called iCIPT2. It's actually a combination of iCI with selection and perturbation. So whatever Hamiltonian you pick up, so we will solve this quantum mechanical equation by using a finite base set. That means we are solving a matrix eigenvalue problem with some known information. And the known information, of course, contained the zeroth order wave function. Then we introduce a wave operator to map the reference function to the excited function. There are various ways to do this: linear ansatz, nonlinear ansatz, and even multilinear ansatz. So now I think it's clear that CI and DMRG are good for static correlation, couple cluster, or many body perturbation theory for good for dynamic correlation. The main problem that electron correlation is the combinatorial complexity. That means the number of determinants goes exponentially. So what we can make use is antisymmetry, spin symmetry, and spectral symmetry, especially sparsity and redundancy. So let me remind you what strong correlation what I have in mind. And this is an energy curve for H2 molecule. Nearby the equilibrium distance, the homolumen gap is very large, so that a single reference is a good, quite a good estimate already. So in this case, so we speak of dynamic correlation only. But when the hydrogen molecule starts to dissociate, we have at least two configurations in this case. So the correlation between the two configurations is called static correlation. Then the remaining higher lying orbitals contribute to the static dynamic correlation. So we have decomposed the overall correlation into static and dynamic components. Then we can classify our chemical systems into 4 families. The first one is that there's no static nor dynamic correlation. That means Hashi-Fock is essentially exact. For the second class is there's no static correlation, as it's called weakly correlated system, DFT, MP2, and so on, works very well. The third family of system is that there's no dynamic correlation, and all of the orbitals are near degenerate. So DMRG presumably represents one of the best choices. However, our daily life, the chemical systems have both static and dynamic correlations. And for this case, so we also have 2 paradigms. The first time is the single reference method. I mean, no matter how you have a near degeneracy or not, you can always start from a single reference and then go to a higher level excitations. Then eventually you can reproduce fully exact results. The second family of method, of course, start with multiple reference, and then you can do lower level excitation. Actually, the multiple reference method just pick up a number of determinants or conformity functions and diagonalize Hamiltonian to get a zeroth order wave function. And this zeroth order wave function already describes static correlation. And the remaining part of the wave function describes static dynamic correlation. Then according to when static and dynamic correlation are treated, we can classify all of the wave function-based methods into 3 families. The first family of method is that you treat static correlation first, then dynamic correlation. Here, the zeroth order coefficients are used to construct the dynamic correlation, but fixed. So there are good examples from iCIPT2, NEP2, all belong to this family. This method, kind of method, of course, static correlation does not say dynamic correlation. The second family of method that you treat dynamic correlation first, then static correlation. And the zeroth order coefficients are not used to construct dynamic correlation at all. So the effective Hamiltonian-based MRPD2 or multi-reference couple cluster belong to this family. So it's obvious that both types of methods cannot, let's say, treat static dynamic correlation in a adaptive manner. So only the third family of method, you treat a static correlation, then dynamic, again static correlation. That means the zeroth order coefficient are used to construct dynamic correlation, but relaxed, fully or largely relaxed. So MRCI, for belongs to this family. Of course, there's still a problem here. So let's denote that NQ is the number of external functions, NS is the number of secondary functions, NP is the number of primary functions, where NP also the number of roots you want. So typically in this set of method, people diagonalize a very large matrix to just get NP state correct. Further, if NP equals 1, you also need to diagonalize a large matrix to get a 1 state correct. So a few years ago, together with Mark Hoffman, we introduced what we call restricted static dynamic static framework. Then no matter how many orbitals, how many electrons you want to correlate, we always diagonalize a 3NP by 3NP matrix. Again, NP is number of state you want. So if you want one state, you construct diagonalize a 3 by 3 matrix. You want 2 states, then you construct a 6 by 6 matrix. Okay. So let's start with the zeroth order function as self calculations. For each zeroth order function, we'll create a first order function for dynamic correlation. So obvious that's the first static, then dynamics. To account for the changes of reference function in the presence of dynamic correlation, we introduce what we call secondary functions. Then we allow them to interact, and to interact, that means we construct and diagonalize a 3NP by 3NP matrix. Okay. Of course, this method we call this minimal MRCI approach we call SDSCI. As computationally, it's scale as a 6th power of the number of electrons. That's because the interaction between the two functions, first order functions. So if we replace the QH2 block with a QH naught, H naught is 0th order Hamiltonian, then we can reduce the scaling down to into the 5th power. So we call this SGSP2. So SGSP2 is a CI-like perturbation theory. So before the diagonalization is taken, we approximate the Hamiltonian matrix elements. Okay. Of course, since we do diagonalization, the method is no longer size constant. However, the size constant error can be readily removed largely. For example, this is for lithium-2 dimer, beryllium dimer, and nitrogen dimer. So after the proper correction, you see the size constant error are removed essentially for both SDSP2 and SDSCI. This is for ground state energies. So we also tested the size constant error for the excitation energies, as this benzene coupled with helium, neon, argon, krypton. So you can see this size constant error in average about several millihartz. I think it is acceptable. And then we also look at the excitation energies of the tier set, some organic molecules. We have 140 singular state, 70 triplet state. I would say the accuracy of SDSP2 and SDSI are very much like NEPP2 and CASP2, and even somewhat better if you look at the spread of the results, right? Of course, these systems are not are really weakly correlated systems. So let me show you another example. This is a spin state splittings of ferrocene. So let's take a MRCI as a benchmark. So you look at the triplet B2 at a printable event state. And these two states are separated by nearly about 8 picomoles. But both CASP2 and NEPP2 predict that they are nearly degenerate. Okay, so only SDSP2 predicts the correct error separation. As you can see, NEPP2 even predicts the lowest state. Actually, this state is very high. Okay, so I want to remind you that SDSP2 is just the extension of, let's say, NEPP2. So NEPP2 treats the 0th order and the 1st order function as by 1-to-1 fixed. Okay, it just treats the 0th order function and the 1st order function as the independent function. Then in addition to the two set of functions, we insert a secondary state. So we diagonalize a 3 by 3 matrix. Okay, so SGSP2 treat single and multiple rules in the same way. So now you diagonalize a 3NP by 3NP matrix. So you get a new vector, right? New reference. Then you can do additional single double excitations for dynamic correlation, and this obviously repeated iterative precision that we call iterative confirmation interaction, so iCI. So let me again show you the example. This H2 molecule. Let's focus on the red curve. The two OH bonds are stretched simultaneously twice. Okay. In this case, Hartree fork is a very poor approximation. So we start from Hartree fork. It takes less 10 iterations to produce full CI. So if you start from better initial guess, like cost 4, then of course the number of iterations gets reduced. Okay, so actually it can be proven mathematically. iCI converts monotonically to full CI from above. Okay, so you can say that iCI is really exact solver of full CI. What's I like as iCI is that at each iteration, actually, iCI produces some physically meaningful results. For example, if for this case, water molecule at equilibrium distance, for example, we start from CF. So we do one-step macro iteration. That means we do single double excitation. We will generate SDSCI. Then if we do micro iteration to relax the contraction coefficients, so we will reproduce uncontracted MRCID. So in the next macro iteration, we will produce uncontracted MRCID2. For example, in this case, we are already lower than the MRG values. Okay, so this is very interesting. Of course, iCI is a very expensive method, just like a full CI, because it's agrees with fly. So far we have not made introduce any cutoff. So the point that if you look at the Hamiltonian matrix element, so this is very sparse. And some block of the matrix are strictly 0 because the Hamiltonian has only two-body operator, and some of the matrix elements are near 0. And some block matrix are partly non-zero, partly 0. So the question is how to select these important configurations a priori. Okay, so how to select the effective configuration pairs, how to select the individual configuration functions. So when you do selection, issue lies that how do you terminate selection? Okay, and how to reuse carbon coefficient to make its calculation faster, and how to reduce memory, so finally, and how to estimate truncation errors. So I think these issues are relevant to all select CI. So we have observed that actually for the two-body, for double excitations, there are some upper bounds for some Hamiltonian matrix elements. Okay, and these upper bounds can be estimated from very beginning and arranged in descending order stored in memory. Then we can use this Hamiltonian estimate to screen out to the important, let's say, double excited configurations. For example, in this case, for a given configuration, these important double excited configurations are never touched. They are very much like a hit pass CI, but they work with determinant. Okay, so after this step, this integral pre-screening step, we also evaluate the first order coefficient. So to prove to measure the importance of Q functions. Then we put the Q function into the, let's say, initial primary space. Then after that, we diagonalize this space and remove those configuration functions with coefficients smaller than the threshold C mean. Okay, and it turned out that our selection is very extremely efficient. For example, compared to a hit bar CI. So in this step, if you hit by CI only consider this integral pre-screening, actually the P1 space, and then you bring in too many Q functions. So after pruned 90%, more than 90% of these configurations will be pruned away. Okay, so it's a waste of time for Hamiltonian contraction and diagonalization. So in our case, so much smaller. So actually, we have tested that our selection is about 20% of the PT2 CPU time, but the hit pass CI type is more than factor 2. Is more expensive than PT2 collection. Okay, so of course, next step is how to reuse the basic carbon coefficient, and this is a crucial point. So for this, we introduced what we call a TUGA approach, tabulated unitary group approach. Let me explain to you that the basic carbon coefficients actually depend only on the relative occupations between the bro and cat configurations. And if there's a common zero occupied and common double occupied do not contribute at all. So after removing these two orbitals, we are left with 7 occupation patterns. So we enumerate each pattern with a code number. So then for all the integrals, actually, if they share the same code sequence, I mean, again, this share same common coefficient. Okay, so then this basic common coefficient can be reused for many 2-dimensional integrals. So we call this approach tabulated unitary group approach. I'm sure that some of you have heard about the table CI approach. Actually, table CI is a more akin to a symmetric group approach. So it involves extensive line-up permutations, but we have no line-up permutation at all. So this flowchart for the selection. So after selection, we do perturbation. Actually, we just recently discovered a particle representation between to establish a connection between randomly selected conformity functions to construct Hamiltonian very efficiently. And for the PT2 correction, we follow Head-Gordon's idea that to split the Q function into disjoint subsets so that you can do parallel computations. So no matter how you truncate the selection, the wave function is strictly has correct spin because we work with convolution functions. So overall, we have only single parameter C mean to determine the accuracy. So let me show you just a few examples. So these are planetary curves of oxygen for triplet, singlet, delta, and sigma. So you can see a big figure. We do reproduce very smooth and curves. Even this region, the 3 curves get closed. And of course, the spectral scope constants comes out very nicely. This is a toy example, okay? But this less trivial example, as this example was mentioned yesterday by Seiichiro. This is called blood test of benzene energy. Last July also, Wenjian Liu invited 8 research groups, basically 8 methods to do the blind calculations for the ground state energy of benzene. And the blue dots represented the 8 blind test results. So in average, it's 863 millihartz, but the method differ by more than 1 millihartz. Actually, during the writing of the paper, some post-blind test results already come out. These triangles, and the average value is still around 863 millihartz. So now the scattering is reduced down to below 1 millihartz. Okay, and all these methods actually, in my opinion, can be classified into 2 families. One is some of the CI type of methods. CI type of methods belong to more static, less dynamic approach. Okay, we rely on a large variational space because we treat dynamic correlation only at a single order perturbation level. But the top cluster approach belongs to this family, less static and more dynamic. As I said yesterday by Seiichiro, in his full cluster reduction approach, he had roughly half number of determinants of our selected CI approach, but still get very good results because he does more for dynamic correlation. So, but if you look at the efficiency, okay, this is rough as a flavor, tells the flavor of the efficiency of all the calculations. You see, it's obvious that the CI type of methods are more efficient than couple cluster ones. Okay, actually, all iCIPT2 has been improved by a factor of 20. So it's obvious that our iCIPT2 is most efficient among all these methods. So let's make a final example. This is called iron cluster. This simplest model of iron-containing enzyme. It has been used by some others guys. Okay, actually, if you think of these 2 irons, each has a 5½ spin, and they coupled to a spin from 0 to 5. Okay, so in total, you have this number of convergence functions. So all energy for ground state essentially agree with DMRG values. Okay, differ by let's say only 0.1 millihartz. But if you look at the excited states, okay, And the lowest excited state come from actually the lowest spin, actually, from this spin state. And it increases from to 0 to 5, it increases steadily. It's six spin states. But for the next 30 states, okay, for the next 30 states, actually scattered in less than 1 electron volt. That means the average separation between these two states is only 0.03 electron volt. Okay, so I don't believe the determinant-based approaches can really handle this kind of complicated spin structure. So actually, let me summarize what we have been doing. Actually, which are the whole of SGS family of methods. So SGS by construction means that we construct and diagonalize a 3NP by 3NP matrix. The NP is the number of states you want. So the generic algorithm method is SGS-PT2. As I told you that before the diagonalization is made, we build an approximation to the QHQ interaction, then we get SGS-PT2. But if you repeat SGS iteratively, then we have the iCI method. Actually, it's a micro iteration. It can be generalized to a method which is called IVI, iterative vector interaction, to partial diagonalization given matrix. In particular, IVI can actually target directly interior roots. I mean, some very high lying roots without accessing the low lying roots. So starting from iCI, when we introduce selection, we call CC. Then of course, we split the selection into 2 steps. So then we have this iCIPT2. Okay. From here we have iCI SF. That means iCI as a solver of cost-safe problem. Actually, if you think about the Hartree fork, it's also a full CI, just one particle full CI. Actually, then we can generalize the iCI into IOI, iterative orbit interaction, as a bottom-up solver of the Hartree fork problem. So this measure start to work now. And from IOI, we are developing a new method which I call ICAS, imposed CAS. As this is the automatic selection of CAS space. And more importantly, so this CAS space is guaranteed to be the same for all the geometries of complex systems. I think this is a very unique feature. Then after we finish the iCISF, of course, we can do perturbation, especially SGS-PT2 or iCIPT2, okay? So this is the whole family of SGS methods. I'm very happy with this kind of discovery. So in the we can switch on relativity and even QD effect, okay? So then in the end, I want to acknowledge my collaborators of the collaborated with Ms. V on these topics from the very beginning. And Ning Zhang is extremely smart PhD student from Peking University. He implemented the iCIPT2. And Professor Yibo Lei implemented SGS-PT2 with me. Thank you for your attention.
Okay, so I didn't get any the questions on the Q&A window. Is there any questions from the audience now? If not, I'm just going to ask very simple questions, Professor Liu.
Yeah.
So your programs are offered publicly?
Yes, our code, I mean, is not user friendly. It's just a platform for developing new methodologies. Mm-hmm. But we are trying hard to push our code, which is called BDF, Beijing Density Function Package. So if you work in the regime of relativistic electron structure theory, you might hear of our code. Actually, we are trying to polish the code such that it can be used for others. Actually.
Okay.
Yeah.
All right. Thanks very much. Any other question?
Can I?
Go ahead.
Can I ask one question?
Yes, please.
First, thank you very much for your interesting talk. I really enjoy. I'm curious, in practice, roughly how many orbitals can be utilized for the iCIPT2 method?
So far, we have tested, let's say, 100 orbitals also. But I mean, for real large systems, of course, you have to work with localized orbitals, and then do proper screening of the two electron integrals. Then you can do somewhat bigger. Okay. For example, what I have no time to mention is the iCAS. The method is really generate localized CASF orbitals automatically. So in that case. Of course, for large molecule, I think you probably are more interested in relative energies, right? Not of the absolute energies. If you look are interested in relative energies, then I think we have a good chance to do bigger systems by cutting down, for example, the P2 step. We can introduce a cutoff for perturbation step, and then we really can do a larger molecule.
And I'm also curious what the bottleneck of this method is. Maybe some memory or.
That's a good question. Actually, so far, I mean, we still suffer from a memory burning. But we plan to introduce a semi-stochastic approach to evaluate the PT2 correction. Then the memory will be reduced. I mean, the memory is no longer an issue.